y over dx squared, that's our second derivative, times y cubed equals 0. Oh my goodness. All right. Now, I'm trying to find the second derivative, right? So solve for it. You got to get it by itself. So let's get this thing right here isolated by itself on one side of the equation. So to do that, I think what I'll do is I'll move both these terms to the other side. So we'll have the second derivative. That's our second derivative times y cubed equals, when those other terms come to the other side, they become minus right? So just bring this whole thing over, bring this whole thing over, so they're both subtracted. What now? Divide by y cubed. Yep. So take this, divide the whole side by y cubed. It's gone. And that's what the second derivative is.
We just leave it like that? We can't simplify any further?
Yeah, so this answer, if you go check the back of the book, that's not going to be the answer. Yes?
So then do we have to plug in the first derivative?
Yeah, so exactly. So think about this. Remember the problem we just did, right? We were trying to find the equation of the tangent line, and I gave you a point, right? So the only thing that, if you go back to what we did last class and into today, anytime we were doing this implicit differentiation, when it came to the slope of tangent line, all you needed was the x and the y, right? If you had x and y, you should be able to give me that derivative. Here, what is it telling us we need to know the second derivative? We need to know what x is, we need to know what y is, and we need to know the first derivative at that point. So what I'm going to do is I'm going to go back up here. Remember when we had this up here? Could you solve that for dy dx? Yes, you could. Solve that for dy dx. I'm going to do it right here. Move the x cubed to the other side. You get negative x cubed, right? And then divide through by y cubed. So dy dx would be negative x cubed over y cubed, wouldn't it be? Do y'all see how I did that? Move the x cubed over, then divide both sides by y cubed. Let's take that answer and plug it in right here. Let's plug it in right here. So the second derivative of our curve with respect to x is negative 3x squared minus 3y squared. And now I'm replacing this with negative x cubed over y cubed, right? But I have to still square it, don't I? And then all of that over y cubed. All right. Let's clean that up. Let's clean that up. May as well do a little bit of algebra here. This is negative 3x squared minus 3y squared. And now let me square that. If I square that fraction, x to the 6th over y to the 6th, and then all of this is still over y to the 3rd. I'm going to keep going because I can put some stuff together still. Negative 3x squared minus 3. Okay, let's see what happens with these y's. That's really a y to the 4th on the bottom, isn't it? And an x to the 6th on top. X to the 6th. I'm going to write it like this, over y to the 4th. And then all of that over y to the 3rd. What do you want me to do? I saw you.
Bring the y cubed up.
How do you want me to do that? Flip it, right? So look at this as over 1, and then like that? Okay, so bring that up, make that 1 over y cubed. And that's multiplication, and then I'm going to just distribute through like that. Is that all right with everyone? Okay, so this flipped and became that. Let's multiply that through. This times that gives me negative 3x squared over y to the third. And then minus 3x to the sixth over y to the seventh. Right, so here to here, you just get a y cubed on the bottom. Here to here, it's the same top, but the bottom becomes y to the seventh. Yeah, that look better? All right, so you get to this point. I don't know, do you want to do anything more? You can take a negative 3x squared. So you want me to maybe put these together into one fraction, or can I take out, can I factor anything out right now? You want common denominator? Let's do common denominator, then I'll factor out a negative 3x. So we have to have the same denominator here. So I would need what here? Top and bottom by y to the fourth, like that. So we've got what? Negative 3x squared y to the fourth minus 3x to the sixth over y to the seventh.
Oh, yeah.
Yeah, I mean, you could pull a GCF right now if you want, negative 3x squared out.
Yeah.
I mean, I'm done. I think I'm happy.
That'll be like the mathematical answer, right?
Well, yeah, I don't think they'll have it for an even. This is an even problem. So there's a lot of algebra manipulation, algebraic manipulations in here, but the thing is, do not have your answer still have dy dx in it. Get it in terms of x and y, all right? And if you want to clean it up after that, great, but at least get it within.
That would be fine.
Like even this is like you're at a point where right now all you have to give me is x and y and you're good. All right, let's get into the next section. All right, I'm going to start this section out actually by asking us to still do some implicit, all right? But I'm going to give you something new to look at. Y'all ever see this before?
Yeah.
Of course you've seen that, right? That's the formula for the area of a circle, right? It gives you a relationship between two things, right? If somebody gives you a circle, right? Yes, you can put 2.7. This right here, this formula gives you a relationship between area and radius of a circle, right? So there are two things that are connected to one another, right? You have a relationship between A and R, yes, for a circle. All right, let me ask you right now to find dA dr. Now, look, I mean, this is just like we were doing before. We had variables, but we were using x and y, weren't we? X and y. Here we got a and r. Pi is a constant, isn't it? Pi is a number. So if I ask you for dA dr, that means you're going to take this equation, take the derivative on both sides with respect to what? R, the variable on the bottom here. So I'm going to take that equation, take the derivative with respect to little r on the left side, and then the derivative with respect to r on the right side. Right? Now look at the left side. What's dA dr? right? If you just push that a up on top, what's the derivative of a with respect to r? Well, that's what we want, right? That's what we want. So I'm actually happy to see that. That's just dA dr. And what is it equal to? Okay, over here, you have that pi next to the r squared, right? So the pi is a constant. It'll just come with us for the ride. So I'll just put a pi out here. And now I need to take derivative of the r squared. R is a variable, right? Not a constant. So what's derivative of something squared? 2 times r, right? 2r, and then times d, the derivative with respect to r of r, which should just be 1, right? See, this right here, again, is where we were having that y dy dx. Same idea, just we're differentiating with respect to r this time. So derivative of r squared is 2r, dr dr. Dr dr turns into 1, doesn't it? So this is just 2 pi r, if you want, 2 pi r. Did you raise your hand? Were you raising your hand? No? Okay. Yeah, I would normally write 2 pi r. So let me write this down. What we're saying is that dA dr is 2 pi r. Now, you might recognize that as the circumference. Okay, that's irrelevant. That doesn't have anything to do with this problem. It happens to turn out that way right here, okay? So look, I've got two formulas. This right here says that if you give me r, right, I will give you the area of a circle, yes? And then that says that if you give me r, I can then tell you what? The rate at which the area changes with respect to r. What does this mean? This right here means that if I were to nudge r just a little bit, like let's say this is the r. If I were to change the r and make the r grow just a little bit, do you agree the area would change a little bit? Yes? That is a formula that tells you how much that area is going to change if you change the r by a little bit. So if I change r, let's say this is the radius. Let's say I take that and I add 1 to that radius. Now the radius is what? R plus 1, right? How much did the area change by? Well, how much did I change r? What was my new radius? R plus 1. So whatever the radius is plus 1 would go in here, and that would be the change in area. Okay? Bessie, another better example. Let's say I had a circle of radius 3, and then I increase that to a radius of 4. Right? So it went from 3 to 4. This gives me my change in area. Now, let's do the same problem. I'm going to ask you a different question, though.
Did it give you new area? Or
No. It's the rate of change. It's how much the area changed by.
Okay.
With respect to the change in the radius. It's how much the area changes with respect to, it's a ratio. It's the change in the area divided by the change in r. How much did we change r by? 1, so it would just be your change in area. Same problem, I want to know this. What's dr dA? Now I'm asking, how much does the radius change by if I change a by a little bit, right? So if I change the area a little bit, how much does that impact the radius? That's a different question, because now we're going to take this equation, differentiate both sides with respect to what? A. Okay. So I'm doing d dA of a, and then equals d dA of pi r squared. What's the left side this time? It's just 1, right? Because that's dA dA. And now this one right here, the pi can come for the ride, right? Pi can come for the ride. Taking derivative of r squared, the 2 still comes out, 2 times r. But now what do you have? Because of chain rule. dr over dA. which is good to see because that's what I want, right? That's what I was looking for, dr dA. Solve for it, right? How would you solve for that? Divide both sides by, yep, pi times 2r, so you get just 2 pi r over there. Hey, wait a minute, does this make sense to y'all that this is the way it is? If dA over dr is this, then what's that flipped over? Well, it should be that flipped over, right? That makes sense to you? That's not the important part of what I'm doing. The important part of what I'm doing is that I'm asking you to find a different derivative with respect to a different variable, right? So that changes the way you differentiate things. Questions? All right, one more, and then we're going to get into the word problems. I'm going to ask you same exact equation, but now now I want you to find dA dt. And before I actually do it, let me just talk about this. In the first problem I did, I wanted dA dr, right? And we got that. Second one we did, I wanted dr dA. Now I want dA dt. So I want to just talk about what these three things mean. This first one said, hey, look, if I change the radius a little bit, right, how much does the area change? What's that ratio? This one says, okay, think of it different. If I change the area, how does that impact the radius? This one says, if I change the what? Yeah, so t isn't here, right? T isn't here. So what's t? Well, it could be anything. Most of the problems that we're going to do, the t is going to be time. So imagine that you have a circle that's just growing. Like you start a clock and the circle starts to grow. Okay? Starts to grow. What we can do is we can ask, how fast is the area growing with respect to the time? So as the time changes, how does that impact the area? Instead of saying, if the radius changes, how does that impact area? So it is okay to differentiate an equation with respect to a variable that does not appear in the equation. Let's see how it works out. I'm going to differentiate both sides with respect to t, right? So I'm taking derivative of a with respect to t on the left. On the right-hand side, 2 pi r, sorry, not 2 pi r squared, pi r squared. And then you take derivative of that with respect to t. What is the left side? dA dt. dA over dt. Or dA dt. Right? Hey, that's what I'm looking for. Great, there it is. Equals, now the pi comes. Derivative of r squared is 2r. But we're not done. What? dr dt. See, we have chain rule here. 2r, and then derivative of r with respect to t is not 1. It's dr dt. This is the, yes?
So then would you have to go find the derivative there?
Yeah, so if you wanted to know dA dt, what would you need to know? You would need to know the radius, and you would need to know how fast the radius is changing with respect to time. Let me say it again. If you want to know how fast the area is changing with respect to time, I need to know the radius of the circle you're talking about, and I need to know how fast that radius is growing with respect to time. If you can give me that, then I can give you how fast the area changes. But we're about to do this, all right? I just want you to see the main point of this is when you have an equation, of course you can differentiate with respect to one of the two variables in there, but you can also differentiate with respect to a variable that's not in there, all right? Okay, I think we're ready. Let's go to my notes. A lot of words. We've now reached one of the most exciting and useful sections of this class, meaning this is the stuff that we actually use in the real world. Okay? Now the problems we do here are not going to look like real world problems because we're just going to try and learn what's going on here. So we're going to use basic shapes, basic ideas, and the things we're going to be asking, you're going to probably be like, why in the world would you ever want to know that? That's the important part is, can we set up the problem and execute the math, all right? So of course we don't start with the most complicated things. So we now study applications of the differentiation to related rate problems. This will be one of the most challenging sections of the course. I only say that because historically, if I take a vote at the beginning of Cal 2 and say, what did you not like about Cal 1? Students will say related rates and optimization. Those are the two things that always come out of their mouths. So I'm just telling you what everyone has told me. And when I was a student, I didn't really like this as well. All right, students struggle in this section because it involves word problems. These are intimidating, I understand that, but I assure you there is some systematic approach that we can take to these problems, all right? It's not going to be cookie cutter, every problem's done the same way, but there's at least some sort of format that we can try and follow, all right? The big thing is, once we figure out how to translate the problem into the math, then the math part of it's the easy part, the differentiation. As you will see, there is an expectation here, which again makes part of the challenge for you. There's an expectation that you know some geometry, trigonometry, basic formulas for areas, volumes, etc. And so if you're at home doing homework and you're trying to figure something out, you know, you've got Google, you've got all these things. Remember your formula sheets. Can I see that real quick? Reference page 1, very first page, has formulas for areas of circle, triangles, volumes of spheres, surface areas of cylinders, cones. There's a lot of things on there. Not everything you need is on there. Some of it we'll have to kind of dig up out of the archives of your brain. But that's kind of what makes it hard as well, because there's things that I assume that you know. All right. So we're going to begin slow and we're going to move into this. Now, on our, let me see if I can find this. I handed some stuff out to you all first day, right? But I didn't give you all this. Hold on. Where is it? Uh-oh. Where is it? All right, let me find it real fast. All right, I'm going to have to do it the hard way. Let me just go ahead and show it to you. I was going to print some out today. I should have, but I didn't. So I'm going to go into Canvas and show you where to find this. It sucks. Faculty, we have to do two-step verification every time we log in. It's a pain in the ass. Faculty, no, courses, sorry. Summer. This should be you. Yeah, that's us. Okay, so under your files, formulas you can have on exams, there's this thing called related rate worksheet. I'm going to download it because I'm going to use it today. So I'm going to go back to OneNote here. I'm just insert it in here. All right, here it is. So I'll zoom out so you can see in totality what this thing looks like. All right, it's just a page, and it has some instructions on the top, and it has these little boxes, and the boxes are for you to like fill things in as you do these problems. It's a template. It's not, like I said, it's not every problem is going to be perfect with this, but you can print this out and bring it to the exam. I'm not going to print them for you though, all right? You can bring a couple of copies of this to the exam. So the first part of this worksheet on the top, it kind of gives you a recap of what you're supposed to do, all right? First thing we're going to do is we're going to read the problem, right? Try and understand what it's saying. We're going to draw some pictures, all right? We're going to draw some pictures. And we're going to have two pictures. In most of these problems, we're going to have two pictures. Because what's going to be happening in all these problems, there's going to be things that are in motion. And we're going to be trying to figure out how one variable is related to the other. Like the circle, right? If the circle is growing, we want to know how fast the area is growing with respect to something. So we're going to have a picture, a general picture, and then we're going to have a picture of what we call the instant or exact moment in time picture. This, again, will become more clear when I do a problem, but there will be two pictures. One where things are in motion, and one where things are like you've taken a picture and everything's frozen in time. Then you're going to write down what you're given. Anything that you're given in the problem, you're going to list that out. And then you're going to also list out what you want. What are you trying to find? Once you list out what you're given and what you want, you've got your pictures. You're going to come up with an equation. Then you're going to do some implicit differentiation on that equation. Any scratch work we'll put here, and we'll put our final answer over here. So that's the worksheet I'm going to be working off of, all right? First time looking at it, you're like, what the hell? Let's actually look at a problem, okay? Let's get to our first related rate problem. Related rates. When you hear the word rate, what do you think of? Change? Is that what I heard? Change? Like a rate of change? Like a speed, right? Driving down the road, your speed is a rate. Do y'all agree? And the speed is a derivative, right? So this section is about related rates. It's how two derivatives are related to one another. How two derivatives are connected. You need to see the problem. Here's your first one. If the radius of a circle is increasing at a constant rate of 0.5 feet every second, then how fast is the area increasing when the radius is 4 feet? Take a second to absorb the problem for a moment. See if you can visualize what's happening. Circle's growing, right? Circle's growing. It's growing in such a manner that what's increasing at a constant rate? Its radius. So its radius is growing. Let me show you an animation of this. I'm going to speed this up a little bit. Start it over. Okay, imagine that let me freeze it. Imagine you were to connect from the center of this circle to there. That would be the radius, right? I want you to imagine the point right here. Watch that point move across the x-axis. And think about it like a car driving down the road, all right? And I want you to tell me whether or not it looks like that car is driving at a constant speed. Do y'all see the point right here? Start over. Does that look like that's moving at a constant speed? Yes? Okay. Now, that's what this problem is saying. It's saying you've got this circle where the radius is growing at a constant rate. If I stop it right there, that circle has an area, doesn't it? That circle has an area. If I let it jump just a little bit and stop, now it's got more area. Yes? So that little jump from here to here, I increase the area by some amount, right? Let's say I go out a little bit further, like right here. That circle has a different area, doesn't it? Now what if I make that jump a little bit? The area will grow again? Is it the same as it was before, though, on the smaller one? So it's like there's two different scenarios I'm asking you to think about. First one, I had a smaller circle. I let the area grow a little bit, and now I've got this bigger circle, and this is how much the area grew by, right? But if I were to start with a bigger circle and let the radius grow a little bit, just like I did over here, right? If I make that the same amount, this circle, I added a bunch more area, didn't I? Because that ring is much bigger. So even though the radius jumped by the same amount in both those pictures, the additional area is different in each of those pictures because of the size of the circle in each one. Do you all see the difference? What we're interested in this class and in calculus is neither one of these scenarios. We want to know at some point at that instant how fast the area is growing. It's like the problem when you look down at the speedometer and you're trying to figure out how fast you're going. We ran into the problem of, oh wait, you can't talk about speed at an instant because you get 0 over 0. That's exactly what we're trying to do here, is we're saying as this thing moves across, the radius is growing constantly, right? But what about the area? Is it growing constantly? No, right? The area is not growing constantly. So I would like to know at a specific point how fast the area is growing. I want to know the rate at which the area is changing. I hope you can wrap your mind about it. I want to run through this animation one more time. This time what I want you to do when you look at this is I want you to, we've already established that the radius is growing constantly, right? I want you to pay attention to the area. Watch the area. Watch how slow it's growing initially. Now watch how fast this number is going to start getting bigger. It's speeding up, isn't it? Isn't that speeding up? That's staying the same speed. That's speeding up. In the beginning, it's growing 4, 5, 6. I think do y'all see it or no? Yes? Okay. I hope all the geometry there makes sense. Let's get to the problem, because you won't have pictures and things like that on the test. You'll just have this, all right? All right, jot that information down. Just put somewhere on a piece of paper, radius is growing at a constant rate, 0.5 feet per second, or 1/2 foot per second, however you want to say that. Write down what the question is. How fast is the area increasing? How fast is the area increasing when the radius is 4 feet? All right. Here's my sheet here. First thing I'm going to do is I'm going to draw some pictures. Now, when I draw my pictures, it does not matter which one I draw first. All right, so I'm just going to draw the general one. I've got a circle, right? And in this general picture, imagine that the circle is in motion. So that circle has some radius. I'm going to call it R, right? It's growing. It's changing, isn't it? That radius is growing. Now, in the exact moment in time, what does it say? You wrote